Hello and welcome to lecture 57 of the course Computational Complexity. Right. So in the past couple of lectures, we saw the topic of communication complexity. In this lecture and the next, we'll see an application of communication complexity into circuit complexity. Right. So we'll see how communication complexity in a certain setting will imply lower bounds for circuit complexity. Okay, so in order to get started, let me define communication complexity of relations. So far we have seen communication complexity of functions where there is a function f that is to be jointly computed by Alice and Bob. But here we are going to talk about relations. So suppose there is a relation R that is subset of x, y, z. So think of x and y as the same x and y, that x goes to Alice, y goes to Bob, and z being the output. So in the case of a function, for every x and y there is a unique z, but in the case of a relation there could be multiple z or no z as well, right? So the goal is x is given to Alice, y is given to Bob, and then they have to determine a z such that x, y, z is in the relation. So if this relation is a function, it is just like computing a function, just that now we have a slightly more generalized setting. There could be multiple z's that satisfy the that satisfy the condition, right? And there could also be no such z. In that case, we do not care what the output is. Okay. So if it was a function, then z would be unique for a specific x and y. But since it's not a function, there could be multiple such z. And deterministic communication complexity of the relation is the worst case cost of the best protocol that computes this relation. Okay, so that is denoted as usual by the symbol dr. And one example is the so-called universal relation. Okay, so universal relation is x is the set of all n bit vectors, y is the set of all n bit vectors, and they have to output z, which is like a number from 1 to n. And the number that they have to output is, if Alice and Bob are given two strings x and y such that x is not equal to y, then they have to output an index I for which the ith bit of x is not equal to the ith bit of y. Okay, so they have to output I such that xi is not equal to yi. Okay, this is the objective. Of course, when Alice and Bob are given the same x is equal to y, then we don't care what they output. So just like we had a matrix for the functions, where we computed functions, we could have a matrix for the relations. Right? So here we have a 8 by 8 matrix. So the rows and columns are indexed with 3-bit numbers and possible responses for the universal relation. Right? So if you see the bottom left corner, the square that I'm highlighting now is for all the 4 by 4 16 values here. Alice has input, the first bit of Alice is equal to 1 and the first bit of Bob is equal to 0. So since they differ in the first bit, the answer could be 1. And similarly in the top right corner here, for all the 16 entries, Alice's first bit is 0 and Bob's first bit is 1. So since they differ in the first bit, they could output 1 here. And if you look at this square, for instance, the small 2 by 2 square, Alice's second bit is 1 and Bob's second bit is 0. So they output 2 as the answer because they differ in the second bit, right? And so on, and you can verify the rest of the entries here. So this is a picture of the matrix corresponding to R, the relation, the universal relation, what they can possibly output, and I have actually, it is already like separated into monochromatic rectangles, right? So this is just to see how a protocol, so from this you can possibly see how they may execute a protocol, right? So and one observation is that for the universal relation, there is always an n plus log n bit protocol. right? So Alice can send entire X, right? So Alice sends X, and Bob sends Z from 1 to n. So X requires n bits and Z requires log n bits, right? So that's why this is n plus log n protocol, and this is a very straightforward protocol, right? This will work for any relation, not just this relation. Like as long as, so instead of log n, it should be log of size of Z, right? Okay, but another thing to note is that there is a lower bound for this universal relation of n minus 1. Why is this? This is because you can compute the function not equal to, okay, so this is complement of equality, right? It's just the opposite of equality. So given a protocol for universal function, we will show how to compute equal and not equal to. So not equal to and equal to should have the same complexity, right? Because it is just flipping of the answer. So if they know that the function is not equal to, then they know that it is equal to also. Perhaps it's easier if I just say, if I don't say not equal to, I just say equality. No, maybe not equal to is necessary. Okay, complement of equality. So we'll see how we can determine not equal to from the universal relation. So suppose suppose we have a protocol for universal relation. That means if X and Y differ, then Alice and Bob can identify using the protocol for universal relation which bit they differ on, right? That is the universal relation. So given X and Y, using du bits, so if the assumption is that there is a protocol for universal relation, right? So using du bits, Alice and Bob can execute a protocol and identify I, the bit where they differ, the index where they differ. And now that they know the index where they differ or they potentially differ, they can send xi, Alice can send xi to Bob and Bob can send yi to Alice, right, to each other. So now that they know each other's ith index, Alice knows yi, Bob knows xi, and then they can compare whether whether their Alice can check whether xi is equal to yi, Bob can also check whether xi is equal to yi, and then that's enough. Both of them know that xi is equal to yi or xi is not equal to yi. If xi is not equal to yi, then x and y are not equal. If xi is equal to yi, then well, they are equal, because the whole thing worked on the assumption that they were not equal, and that's why we are getting the error. So what is the complexity of this protocol, right? The complexity of this protocol is the complexity of the protocol for executing universal relation or computing universal relation du, and after which they send xi, Alice sends xi, Bob sends yi. So 2 more bits after du, right? So this is the complexity of this protocol, and this is one protocol for not equal to. So deterministic complexity of not equal to is at most du plus 2. Okay. But at the same time, using lower bounds for equality, we can also say that deterministic complexity for not equal to is at least n plus 1. Right? So we know that deterministic complexity of not equal to is at least n plus 1 and at most du plus 2. And this gives a lower bound for du as n minus 1. So using the universal relation, you can compute not equal to. And so that gives you this lower bound of n minus 1, where the upper bound, the trivial upper bound, is n plus log n. In fact, this has been improved later. I think n plus 1, n plus 1 by I think Tardos and Zwick. But anyway, I'm not getting into that. Okay, so this is just an example of what is communication complexity of relations. Okay, so in this lecture we will see how communication complexity of relations, how using that we can get a circuit lower bound. Okay, so lower bound for the depth of circuits, not the size. So far I think we have seen size based lower bounds, but this will be a depth lower bound. Okay. So you may recall that a circuit is a tree. So in this lecture we will assume binary tree. Okay, and the depth of a circuit is the length of the longest path from the output, which is the root of the circuit, to an input. Okay, so if you have something like this, this is the depth of the circuit. Suppose this is the longest path. This is the depth of the circuit, and this is denoted d of c, the depth of the circuit. And the depth of a function, right, d of f is the depth of the smallest circuit that computes this function. Okay, so d of c for the smallest, which for the c that minimizes this. Okay, so depth of a function is the depth of the smallest circuit that computes that function. So we have seen circuits, we know what this is. Okay, so now let us define the crucial relation that will help connect communication complexity of relations and circuit depth of circuits. So what we will do is, given a function, okay, a Boolean function, normal Boolean function, which is on n bits, right? So this function is on n bits. We will define what is called a Karachmer-Wigderson relation. Okay, so this is because it was first seen in a paper by Karachmer and Wigderson. Okay, so what is a relation? The relation is this. So you separate the domain of f into 0 inputs and 1 inputs. So let x be all the 1 inputs, meaning all the inputs, all the 0 1, so 0 1 power n inputs, which give out give the answer 1, and y be all the 0 inputs. So both, so just for sanity check, I'll just say that both x and y are in fact subset of 0 1 power n. In fact, they are not just subset, they are disjoint, because for a specific string, either it is f of x is 0 or f of x is y, right? And every small x is either in capital X or capital Y. So it's a partition, right? So in fact, this is true. X intersection Y is the empty set, and X union Y is 0 1 power n. Right? All this can be seen, so you can check all this. This is just to make sure that you understood this correctly. Now we define the Karachmer-Wigderson relation, also called RF. Right? So it is like the universal relation, but slightly different. So in the universal relation, we allowed it is 0 1 power n cross 0 1 power n cross 1 2 3 up to n. But here the Alice input, or the x, is just the 1 inputs, y is just the 0 inputs. Okay. So suppose Alice got string small x, which is a 1 input. So Alice got x such that f of x is equal to 1, and Bob got y such that f of y equal to 0. Obviously x is not equal to y, because x is 1 input, y is a 0 input, and then they have to output an index where xi is not equal to yi, right? So just again to add, f of x is equal to 1, f of y equal to 0, right? This is what we can infer from this, and they need to together determine I is such that xi is not equal to yi, right? So just an example, so perhaps just to see this better. So let us say f is this. Okay, so f of z is equal to this. F of z, maybe I'll just say z is equal to this. So z1 or z2, z1 and z2 or z3 whole or of z2 or z3. Maybe I'll just rearrange these terms so that it's in one line. Maybe it's okay. This is okay. So here it's also drawn in a circuit fashion, Z1, Z2, Z3. So Z2 and Z3 appear twice here, but that's okay since we are computing the same function. Okay. So there is an OR, and the left hand side of the OR, the left subtree computes Z1 and Z2 or Z3, and the right subtree computes Z2 and Z3. Okay. So now let's see which inputs give out what. So which are the 1 inputs here? So for a 1 input, either Z2 and Z3 should be 1, right? The second part should be 1, which means anything that ends in 1 1. So 0 1 1 and 1 1 1 are 1 inputs. And which are 1 inputs? So 1 inputs are zero 1 1 1 1 1, and if Z2 and Z3 are not both 1, this is an AND, this is an OR here, this is an OR here. So even the first term could be 1. So the first term is Z1 and Z2 or Z3. So either Z1 has to be 1 and either Z2 or Z3 has to be 1. So you could have 1, you could have 1 1 0 or 1 0 1 or 1 1 1, which is already written. Okay, so these are the 4 1 inputs. So you can verify that these are the 4 1 inputs, and I am writing them as the columns of this matrix over here. So if you just see, I've written them down as the columns of this matrix. The columns are the rows are indexed by these 4 values, which are the 1 inputs, and everything else is 0 input. And you can indeed verify this, that the rest are 0 inputs. Verify meaning you can just plug them in the circuit and see that they are all the output is 0, and the columns are indexed by the 0 inputs in the above matrix. So now we need to again, so now it's not a, notice that it is not a 2 power n by 2 power n matrix. It is like, in this case it's a 4 by 4 matrix, but it depends on how the 0 inputs and 1 inputs are distributed, right? So 2 power n here is 8, but then 8, in this case it's a 4 by 4, but it could also have been a 5 by 3, if 5 cross 3 matrix, if there were 5 1 inputs and 3 0 inputs, right? And again we have to, the same thing as universal relation, we have to determine an index where x and y differ, and this is one way to partition it. So notice that for some entries there are multiple correct answers. So for instance, especially if you look at this entry here, anything would be okay here, because the column is indexed by 0 0 0 and the row is indexed by 1 1 1. So 1 or 2 or 3, anything would do. But in this case it turned out to be more convenient to have 1, because the rectangle partitioning is better in this case. Okay, so this is the matrix corresponding to the Karachmer-Wigderson function relation corresponding to this function. So Karachmer-Wigderson relation is obtained from a function by classifying it into 0 inputs and 1 inputs. Okay, and the goal is to together collectively identify an index I such that xi is not equal to yi. And in this case there will be no don't cares, because we will not, all xi's are different from y, all x's are different from y's. So it will not be a situation where x and y are the same. And the main theorem by Karachmer and Wigderson is that whatever function we take, the deterministic communication complexity of the Karachmer-Wigderson relation, which I denote by d of Rf, this is equal to the depth of the function, meaning the depth of of a circuit that can compute the function. The smallest depth circuit will have depth equal to the deterministic communication complexity of Rf. So this seems very, very interesting and somewhat surprising, because on one hand we have this relation and then there is this communication between Alice and Bob. On the other hand, we have the circuit computation model and then just computing of a certain function. And one would think, how on earth would the communication complexity bound translate into a circuit complexity bound? But in fact it does. So let's see the proof why this is the case. So we prove it in two parts. First, we show that the deterministic communication complexity is at most the depth. Right, this is part one. Right, deterministic complexity of the relation is at most the depth of the function. And the second part, we show that the depth of the function is at most the deterministic communication complexity of the relation. So it's like we prove two inequalities, and that's how we get the equality bound. Okay. So how do we get the first inequality? So what we do is to, given a function or given a circuit for the function, okay, so we start from a circuit. From that we will build a protocol for the relation, okay, and as long as we started with the circuit for the function f, we will ensure that we get a protocol for the relation Rf, okay, and so and we will get the protocol in such a way that the complexity of the protocol is equal to the depth of the circuit. So I could have chosen any circuit that computes f. So I could choose the circuit of the smallest depth that computes f. So I could choose a circuit of depth df, which means I get a protocol of complexity df. So, and this is an upper bound. This is one protocol of complexity df. So this, hence the deterministic communication complexity is upper bounded by the complexity of this protocol, which is df. Right. So I hope the high level picture is clear. Now all that we need to see is, given a circuit that computes f, how do we get a protocol for the communication complexity of Rf? So what we do, so maybe I will explain here. Okay, what we do is I have just drawn the same circuit, copy pasted from above. What we do here is to, from the circuit we will see how to modify it into the protocol. So the circuit will look something like this, and we will transform the circuit into a protocol tree. That is the idea. So let us traverse from the top down, okay. And so at the top, this entire circuit computes, the top gate computes the function f, right? This computes the function f, right? So what we have here, we know that f of x, where x is Alice's input, is 1, and f of y is 0. And we will make sure that at every stage we are every node, like, so this particular node, let's say it computes g, this particular node, the left child of the root, we will ensure that g computes a function, right, such that g of x is 1 and g of y is 0, and so does every node in the circuit. So we will make sure that at every node in the circuit satisfies or computes a function such that g of x is equal to 1 and f of g of y is 0. So let us see how this happens. So at the base case is the root. At the root we already know that, because of the problem statement, f of x is equal to 1 and f of y equal to 0, where x is Alice's input, y is Bob's input. So now there are two cases. So we will go down, and by induction we will do it. So we are at a certain node, and we want to say something about the children nodes. So there are two children. It's a protocol, it's a circuit of fan in 2, right? So we want to say something about the children. We want to say that the children gate also satisfies this this particular statement. This is the inductive claim. At every step, we ensure that we are at a node that computes a function g such that g of x is equal to 1 and g of y equal to 0. Suppose the current node is an OR gate. Okay, so in this case, the root node is an OR gate. Okay, so we will transform it into something where Alice speaks. So we will say Alice speaks here. Okay, OR gate is where Alice speaks, and AND gate will become places where Bob speaks. Okay, so I'm not gotten there, but I'm just saying. Okay, now Alice, what would Alice reply? Now suppose f, this is an OR gate, so let's say the corresponding functions of the two children are f0 and f1. Okay, so suppose this is f0 and this is f1. Okay, and we know that f of x is equal to 1 and f of y equal to 0, right? We know that f of x is equal to 1 and f of y equal to 0. So f of x is equal to 1, so I could write that as, so, and f is f0 and f0. So what does this mean? This means that f is f0 or f1, right? That's why the top is f, the children are f0 and f1. So f0x or f1x is equal to 1. So the OR of f0x and f1x is equal to 1. This means that either f0x is equal to 1 or f1x is equal to 1. Okay, and the next thing is that f0y and f1y, the OR of these two things is equal to 0, because fy is 0. Now if OR of two things are 0, this means that both of them have to be 0. So f0y is 0, f1y is 0, and either f0x is 1 or f1x is 1. Both also could be 1, f0x and f1x, both of them could be 1, but we know for sure that at least one of them is a 1. Okay, so either for f0 we have that, so whichever input is held by Alice, right, either f0x is equal to, so either for f0x is equal to, so whatever input is held by Alice, let's say that is x, for that x, either f0x is equal to 1 or f1x is equal to 1. So now Alice will say 0 if f0x is 1, and Alice will say 1 if f1x is 1, right? If it is, if both of them are 1, she could choose any one. Let's say she says 0. So there is an I, so I being the subscript of f, such that fix is equal to 1, and whichever I she chooses, fiy is 0, right, because f0y and f1y are both 0. So whatever is that I, Alice sends that I. So she sends that I. Similarly, if the current gate is an AND gate, right, Bob speaks. Why is that? Just like what we said before, we know for sure that, so if it's an AND gate, then it will be like this. Let's say f is computed at that gate, where f is f0 and f1, and we know that f0x and f1x is equal to 1, so which means f1x and f0x and f1x are both equal to 1, and since the AND of two quantities is 0, f0y and f1y is equal to 0. This means that one of f0y or f1y is 0, right? At least one of them must be 0, otherwise the AND should be 1. So now Bob will send, so now Bob knows this because x is 1 for both. So Bob will tell which is the y for which f0y is 0 or f1y is 0. So which is the I for which fiy is 0. Bob sends that I. Okay. So this is how we transform the circuit into a protocol. So all the AND, we said what we said that Alice will speak, and we said what Alice will send for at this node. So initially they held x and y. Alice held x, Bob held y, such that f of x is equal to 1 and f of y equal to 0, where f is the function computed at the root node. Then they will move to one of the nodes which satisfies, let's say they move to the left child. So we know that for the input that they hold, f0 of x is equal to 1 and f0 of y is equal to 0, and then they will keep going down and down and down till they reach a leaf, right? So now the question is, here we have a function that is computed by we have a circuit that computes a function. Now in a protocol, they have to output something at the leaf, right? So when they reach the end of the leaf, that leaf should correspond to something, even though they don't really output something, right? So what is the entry that the leaf corresponds to? So if they are at a leaf, the leaf will be labeled with either something called Zi or Zi complement, where so basically the input string is Z. Either the leaf will involve Zi or Zi complement. So here it's Z1, Z2 or Z3. There is nothing negated here, but if there was a negation, it could be there in the circuit here. Okay. So one more point is that what we can do is to if there is a NOT gate anywhere in the circuit, we could push that NOT gate down using De Morgan's laws, and we will get a circuit with purely AND and OR gates, such that the NOT gates will be only appearing in the input level. So now if there is a NOT gate here, if I want to have a NOT gate here, sorry, let's say if I want to have a NOT gate here, right, I may as well change it to something like this. I may as well push it down to the input bit itself, so Z3 complement, right? So I can do something like this. So there will be no NOT gates in the circuit. There will only be inputs that are negated or non-negated. So when we are at a leaf, the leaf either says Zi or Zi complement. Now we need to think in terms of the protocol, what will we output at the protocol level, right? So we need to say some I, the index I for which xi and yi differ, right? So what we know is that if the leaf is labeled, so because of the induction so far, if the leaf is labeled Zi, right, then that means that the input is such that, so the function computed at the leaf is just Zi, which is the ith, the symbol at the ith index. Then we know that xi is equal to 1 and yi equal to 0 if the symbol is Zi at the leaf. If the symbol at the leaf is Zi complement, then we know that xi is 0 and yi is 1, because that's why xi is equal to 0 for any string with xi is equal to 0, Zi complement is 1 and yi, and for any string with yi is equal to 1, the yi complement is 0, right? So in either of these cases, we will output the bit I. So we check whether what the leaf of the circuit indicates, right? So if it is either Zi or Zi complement, we will set the leaf of the communication complexity protocol to output I, the index I, and that completes it. So using so the proof was kind of descriptive. The correctness was kind of included in the procedure, right? So starting from a circuit for the function f, we converted the circuit into a protocol such that this protocol is for the Karachmer-Wigderson relation of the function f. So this means that the deterministic communication complexity of the relation is at most the depth of the function. So again, how many bits are exchanged in this protocol? It's exactly the depth of this tree, the depth of the circuit. So if it is this, then you can check that they will exchange at most 3 bits. and perhaps you can work out some small examples like this and see whether it checks out correctly. So the number of bits exchanged is the depth of the circuit. So the deterministic communication complexity of RF is at most the depth of this circuit, but the depth of this circuit is but I could choose the circuit of the smallest depth, right? So deterministic communication complexity of RF is at most depth of the function. So that is one direction of the proof. So where we got a protocol from a circuit. The other direction is the opposite, where given a protocol for the Karachmer-Wigderson relation, we will construct a circuit for the function. Okay. So in fact, what we do here is kind of like the reverse of what we did in the first part. So suppose we are given a protocol, we will view it as a tree. Okay. So in the first part, we replaced OR gates OR gates were designated as Alice to speak, and AND gates were designated as places where Bob has to speak. We will do exactly the opposite here. So suppose there is a protocol given. Okay. So we need to convert the protocol into a circuit, right? So we have a tree. And we have places where Alice is designated to speak, Bob is designated to speak, and at the end we have leaves at the bottom, where we know the leaves correspond to some input, so some output, so that the output we know is something from 1 to n. Right. So we need to know how to replace this into a circuit. So all the places where Alice is designated to speak, we will replace it with an OR gate. All the places where Bob is designated to speak are replaced with an AND gate. Okay. Now all that remains is what do we at the bottom. So all the intermediate nodes are taken care, but the leaf nodes, what do they correspond to? In the protocol, it is some output I of the function of the relation. In the circuit, it should be some input to the circuit, so maybe some Zi or Zi complement. Right. So now how do we get that? What should be the labels of the leaves? So we know that every leaf is a monochromatic rectangle, right? This is what we saw earlier when we learned communication complexity. Every leaf is a monochromatic rectangle A cross B, which gives, monochromatic means it gives a certain output I. And we know that if you look at a monochromatic rectangle, right, so which means all of the leaf outputs I, right, so all of this outputs I, something like this. So this means that the inputs differ in the ith bit. Okay, so this means that the inputs here differ in the ith bit. So the first claim is that it has to be the case that for the entire matrix rectangle A cross B, so this is A cross B, all of them output I, so they differ in the ith bit. But further, one more thing is true. The one more thing that is true is that for this entire matrix, either xi is equal to 1 for all this matrix and yi equal to 0 for all this matrix, or the opposite. It cannot be that some entries have xi equal to 1, y equal to 0, some entries have xi is equal to 0 and yi equal to 1, right? Because if you, let's say if this entry has xi equal to 1, yi equal to 0, and this blue encircled entry has xi equal to 0, yi equal to 1. Now consider this purple entry. This will have xi equal to 1 and yi equal to 1, which means it cannot output I. So what this means is that for the entire matrix, either xi equal to 1 and yi equal to 0, or xi equal to 0 and yi equal to 1. It cannot be a mixed match of both. Right? So entire matrix should be corresponding to this. So if it is the case 1, for the entire matrix xi equal to 1, y equal to 0, this means that, so now this function, this leaf can be labeled as Zi, right? And if it is the other case, the second case too, then we label the leaf Zi complement. Okay, so we have described how to construct the circuit. We have replaced Alice speaking places with OR gate, Bob speaking places with AND gate, and we have also explained how to label the leaves. Now all that we need to show, all that remains is that this circuit is a valid circuit for the function. Okay. So the main claim is that for all the nodes of the circuit, so we will view it as both a circuit as well as the protocol to prove this. So consider a node, okay, sorry, consider the tree something like this. Let's say we consider this node. Okay. Now let's say the function computed at this node is G. Okay. And if you view it as a communication complexity protocol, let's say some matrix, the inputs from some matrix A cross B reach this node. The claim is that for whatever inputs contained in this A, right? The claim is that for whatever inputs Z contained in A, G of Z is equal to 1, and for whatever input Z contained in B, G of Z is equal to 0. This is the claim. So you look at any node in the tree, look at the corresponding set of entries that will reach in that node in the protocol, in the communication complexity protocol. Suppose it's A cross B, then for any x in A, G of x is equal to 1, and for any y in B, G of y is equal to 0. Okay. And what would this imply? This would imply that at the, so what function is at the root, right? Whatever function this entire circuit computes. So we have, again, as of now we don't know what it computes. The claim is that it computes f. We have to establish that it computes f. So at the root, what is the matrix that reaches the root? It is the entire x cross y, right? So the matrix that reaches the root is x cross y. Whatever function is computed at the root, we know that f of x is equal to 1 for all the x's in x, and f of y equal to 0 for all the y's in y, which is exactly the function that we were trying to compute. Okay. So the root must compute f if this claim, if this red underlined claim is true. So the claim to be proved is, I'll put this in the green box, this is the claim to be shown. Right? We have built a circuit, or we have transformed the protocol into a circuit, and now we have to show that this circuit works. And I have just described that it is enough to prove this claim. We will use a bottom up induction. Okay. So from the leaf to the root. So let us see what happens at the leaf. So look at here. So this leaf is probably labeled Zi or Zi complement, right? Suppose it is labeled Zi, then we know that by this claim above that whatever functions reaches here, it was labeled Zi because for whatever inputs reached here, xi equal to 1 and yi equal to 0. And if it is Zi complement, whatever inputs reach here, xi equal to 0 and yi equal to 1. So this claim is already true for the leaves by, so when I say the claim, I mean the claim in the green box is true for the leaves by the way the labels were chosen. That was here by this claim. So it is true at the leaves. Okay, we set the values correctly as per the requirement. Now consider any node, any intermediate node, right? Let's say V. Let's say V has children V0 and V1, and let's say F0 and F1 were computed here. Okay, and let F prime be computed at V. Okay. Now in the protocol, let's say it was Alice was speaking here. Let's say Alice was speaking here. Now this means F prime is nothing but F0 or F1, right? Because we replaced, where Alice was speaking, we replaced it with the OR gate. Okay. So now let A cross B be the rectangle at V. So let's say the rectangle at V is A cross B. Okay, and now Alice is speaking here, which means some inputs go to the left side and some inputs go to the right side. Okay. So now what happens is that when some inputs go to the left and some inputs go to the right, what is really happening is that the rectangle is row wise divided into two parts, A0 and A1. So the set A is divided into A0 and A1, and basically this rectangle gets divided horizontally into two parts, A0 cross B and A1 cross B, right? So in the picture I have shown them as contiguous, but it may not be contiguous, they may just combinatorial rectangles, right? They could be in several parts. Okay, so inputs from A0 cross B reach V0 and A1 cross B reach V1, right? Okay. So we know that for all, so we are doing bottom up induction, right? So we know that the inductive claim is true for V0 and V1. What does that mean? Any input that reaches, that is in B, F0 of any input that is in B, so let's say Y is in B, then F0 of Y and F1 of Y are both 0. This is the inductive claim. And hence, even for F prime is nothing but F0 or F1. Even for this, F prime of Y is the OR of two zeros is 0. Okay. So for any Y in B, this is true. Okay. And what more do we know? We know that for all X in A0, F0 of X, F0 of X is equal to 1. In fact, I think I have written this in the bottom. And for all Y in for all X in A1, I have written it here. For all X in A0, F0 of X is 1. For all X in A1, F1X is equal to 1. So this means that for all X in A, so X in A means X is in A0 or A1, F0 or F1 of X equal to 1, but this is nothing but F prime of X. So F prime of X also satisfies, so I messed up here, F prime is equal to F0 plus F0 or F1, F prime of X is equal to Y, F prime of X is equal to 1, F prime of Y equal to 0 for all X in A and for all X in B, for all Y in B. So the inductive claim goes from is true for the level V also. So since we are doing bottom up induction. And the same reasoning is true when for the nodes where Bob speaks. It's just a symmetric argument. Instead of A being cut into two sets A0 and A1, B will be cut into two sets. So it will be a vertical cut rather than a horizontal cut. And pretty much what we said will be true in an analogous manner. So you can work this out. So you can work this out as an exercise, right? So what we have shown is that this circuit that we constructed computes the function f. So the depth of the function is at most the deterministic complexity, because deterministic complexity of the relation, because to start with we could have had we could have chosen the protocol that is the best protocol that minimizes the communication. So the depth of this and you can see clearly, because you can see clearly that the depth of this tree is equal to the complexity of the protocol. So we get that the depth of the function is at most the deterministic complexity of the relation. So because of this, so in fact it's actually a the reduction is very symmetric. Whatever we did in the first part, we are doing the opposite in the second part, but it works. So what we have is that the deterministic communication complexity of the Karachmer-Wigderson relation RF is equal to the depth of the function, which means that so the best protocol, whatever is the complexity, equal to the depth of the best circuit that computes the function. So this is the Karachmer-Wigderson theorem that you can relate. So given a Boolean function f, you can construct this Karachmer-Wigderson relation RF and such that the communication complexity of this Karachmer-Wigderson relation is equal to the depth of the function. This in itself is very interesting, and what we will see in the next lecture is that we will apply this to a specific problem, the computation of matching, the computation of whether there exists a perfect matching in a graph. So, and we will derive depth lower bounds for this problem using this Karachmer-Wigderson relation. Yes, just to summarize, we defined relations. We saw universal relation. We defined the communication complexity of the relation. Then we saw this Karachmer-Wigderson relation and the proof that of the Karachmer-Wigderson theorem that the depth of the Karachmer-Wigderson relation is equal to the deterministic complexity of the relation is equal to the depth of the circuit that computes the function. In the next class, we will see an application of this into matching. Thank you.